All right, so guys, today section 9.2, arithmetic sequences and partial sums. So one of the things I'm sure inevitably that you've already noticed that we often do, or at least the kind of the structural setup with a lot of our chapters here, is that usually that, or oftentimes I should say, that first section is kind of a, hey, this is an overview of the type of stuff we're going to be studying. And then from there, we get more specific. So that's exactly what's happening here today. Yesterday, we talked about sequences and series in general. Today, we're going to specifically talk about the arithmetic sequence, the arithmetic series. Again, when we come back, I know we've got a nice break coming up, so it's not the ideal, let's cover section 9.2 and then take a break and then come back to 9.3. I understand that, but the material being as review heavy as it is, we're going to be fine. But again, if we're going to talk about arithmetic sequences, next thing up is we're going to talk about geometric. Does anybody remember what arithmetic sequences are all about, though? The stuff we're going to talk about today? Ben, what do you got?
This is just like a normal linear function that you just plug in.
Yeah, and I really like the way that Ben said that. If you didn't hear, he said, isn't it just a normal linear function? And that's one of the things that we're really going to lean on here today, is that we're going to try to relate this back to a linear function. In fact, one of our most common equations or formulas, again, we're just going to try to showcase how, yeah, sure, different letters, but this is essentially y equals mx plus b. That's what we have going. Okay? Hudson, I saw your hand was up too. What else? Do you have anything to add on?
I can't top that.
Can't top that? All right. Sometimes the simpler explanation is the one that's the most fitting. Is anybody thinking arithmetic sequence is I'm just going to add the same amount to get from one number to the next to the next to the next? Okay? And that's exactly, that's one of the ways that we want you to think about it. So that common number, it's what we refer to as the common difference, D. Everybody get one of these? Everybody got? Okay. Cameron got two, looks like. But thanks to Dallas. But yeah. All right. So anyway, like I said, arithmetic, it's all about addition. Okay, I'm going to add the same common amount to get from the first term to the second, second to the third, third to the fourth, 200th to the 201st, whatever it is, however big or however small these sequences are, we're going to be adding the same amount to get from term to term. Next week when we come back and we start talking about geometric, same idea, except we're going to be multiplying by a common term to get from one term to the next. All right, so you just received this formula sheet. We're going to be building these as we go. So today we're going to be filling out some of the stuff here in the arithmetic column. All right, but our goals that we have in mind, students be able to recognize, write, and find the nth term of arithmetic sequences. Again, we are going to care much more about the explicit definition than the recursive. We're actually, the way that we're going to find a lot of these things, it's kind of a blend between the two, but again, the rule that we're going to write typically is going to be that explicit definition. Goal number 2, students be able to find the nth partial sum of arithmetic sequences. Again, that's kind of what we just talked about as we wrapped up section 9.1. But again, we're going to take, a very large sequence or even an infinite sequence, and we could find part of that sum. And then number 3, students be able to use arithmetic sequences to model and solve real-world problems. All right, so here it is. This is what we were talking about. Our textbook definition says that a sequence whose consecutive terms have a common difference. Now, the variable that we're always going to use for common difference is D. D for difference, I suppose. So, quite literally, it means that if you have a sequence of values, A1 to A2 to A3 to A4, that if you take any two consecutive values and find their difference, aka subtract them, you're going to get a consistent common number. So we're going to take A2 minus A1. That's the same as A3 minus A2, which is the same as A4 minus A3. Which is the same as A99 minus A98, if we knew what those are. If you take two consecutive terms, once again, we find the difference between them. Well, that's just the amount that you're adding to get from one term to the next to the next. That's what is happening here. Okay? Again, always going to be referred to as D, the common difference. For the majority of the stuff that we are going to be focusing on today, finding that common difference, D, is kind of the biggest thing, the biggest obstacle ahead of us. That if we can find the common difference, then we're in the driver's seat, so to speak, right? So a couple of examples here. It says that here in example number 1, part A, the sequence whose nth term is 4n plus 3. So when they tell us the nth term, they're basically just giving us the definition. They're saying, yep, 4n plus 3. I guess as long as we know what n is equivalent to, we can plug it in and we can find whichever term we want, right? So it goes on to say that for this sequence, the common difference between consecutive terms is 4. So we know that d equals 4. Outstanding. All right. Now, what we can do is utilize this explicit definition, and we can find a sub 1, because all that's saying is we're going to let n equal 1. So as we do the math here, so to speak, 4 times n plus 3, we can do better than that. We know that n is 1. So what is my first term, please? 4 times 1 is 4, plus 3 is 7. Now, question for you. What exactly are we supposed to do for this sequence? So the sequence is okay, so I guess it doesn't exactly tell us how many values. I'm looking for a number. Do we want the first 4 terms, 5 terms? What do we want to do? Doesn't really say, but again, let's just assume that they want 4 terms. So we just did this for a sub 1. Could we do the exact same thing for a sub 2? Yeah, all right, let's do it without writing it out because I'm lazy. But if we were to plug a 2 in place for n, 4 times 2 is 8, plus 3 is 11. We do the same thing for a sub 3, put a 3 in place for n. 4 times 3 is 12, plus 3 more is 15. We can do the same thing for a sub 4. So again, 4 times 4 is 16, plus 3 more is 19. Again, we can definitely keep going, but if we wanted to find the first 4 terms, there they are. Now, we did that explicitly. We literally used the formula to find the first, to find the second, to find the third, to find the fourth. If we wanted to find the 10th, we could just plug an n in, or a 10 in place for n. Whatever term we want, we could plug in. Okay? Could we have done this same exact process recursively? Could we have done the work just as we did here, all of this stuff, and found that a sub 1 is 7? Yeah. We just did that, right? But as soon as we know that a sub 1 is 7, remember that they told us the common difference was 4. So at that point, could we have abandoned the explicit definition? Said, all right, plus 4, plus 4, plus 4, to build the rest of our sequence? So do you see how moving forward, we're going to, again, when it's our job to build a sequence, we're probably going to use the explicit definition to find the first term, but if we know the common difference, we're going to go recursively the rest of the way. Why would we do that? It's faster. It's faster, and it's a little bit, I don't know if I'd say it's more precise, but I mean, it's faster. That's the main reason why. Okay? Again, it's all about just trying to speed up the process here a little bit. So again, same thing here in part B. It says the sequence whose nth term is 7 minus 5n is arithmetic. For this sequence, the common difference between terms is negative 5. So D is negative 5. Uh-oh. Can we have a common difference that's negative? Absolutely. All that's happening is that our values are getting smaller as we go. No big deal. So if we wanted to find the first term, all that this means, n equals 1. So 7 minus, it's going to be equal to 7 minus 5n. But remember, we know that n is 1. So with your help, please, my first term, 7 minus 5 is going to be 2. All right, so if we know that our first term is 2, the common difference is negative 5. We could continue to use that explicit definition, but we also know the pattern, the shortcut here. If our first term is 2, common difference is negative 5. 2 plus negative 5 is? So negative 3 plus negative 5 is? Less people that are answering than I feel comfortable with, quite honestly. Negative 8 plus negative 5 is? Negative 13. We could keep on going with this, right? That's going to be our sequence. Guys, what questions do we have moving forward? Maybe your question is the same as mine. What is this symbol on the right? Don't know. Let me try that again. All right. Any questions, though? Is it all looking familiar? Now, could we have done this if we weren't told that these were arithmetic sequences? If we didn't know that they were, first off, if we didn't know they were arithmetic, they wouldn't have later told us that there's a common difference of 4 or negative 5, respectively. Okay? But again, this only works because we've been given that information that, hey, this is arithmetic, which is then just that I don't know, admittance of, yes, we're going to be adding the same exact amount from each term. Jennifer? Sure. All right, so getting to a formula here. So we say that the nth term of an arithmetic sequence. All right. So please, before you copy everything down here, understand that the way that we're going to address this, the way that every textbook that I've ever seen addresses this, it's for a reason. But this isn't, neither one of these are the formulas that we'd actually want you to write up. Okay, it says that the nth term of an arithmetic sequence has the form a sub n is equal to d times n plus c, where d is the common difference between consecutive terms of the sequence, and c is equivalent to a sub 1 minus d. Okay, so for all intents and purposes, what we're actually doing is d times n plus c, but we're saying that c is actually a1 minus c. This is our formula. This is the true one. This is the one I want you to write down on your formula sheet. This is what we're going to use. This is explicitly how we get to a term. Now, my question goes back to, why in the world do they write it up this way? I'll give you a hint. It has a lot to do with what Ben said at the beginning. On the formula sheet. So this would be the explicit definition of nth term on arithmetic. Exactly. Again, Ben told us that the arithmetic sequence, it's just a linear function. That's all that it is, and he's absolutely right. I understand that all of the letters are different, but does this follow the pattern of y equals mx plus b? Yes. So realizing that d, your common difference, that's your slope. C, the new thing that we're kind of introducing here, a1 minus d, that's your y-intercept. That's your starting point. That's exactly how we want to think about this moving forward. Okay? If we can link this back to linear functions, something that I have to imagine that we feel very confident and comfortable with, then that's just going to make things a little bit simpler. Common difference, that's just your slope. That's all that we're doing. That's going to be the consistent change from term to term to term. All right? So, taking a look at this second example, it says that we want to find a formula for the nth term of the arithmetic sequence whose common difference is 3. So d is 3. And the first term is 2. So a sub 1 is going to be 2. All right, so I can take this information and we can start plugging it in. So a sub n is equal to, what did we say the common difference was? D is 3 times n plus, what did we say a1 is? 2 minus, what did we say d is again? Minus 3. All right. So what do you think? Do you suppose we have to clean things up? That's kind of what this is all about. So a sub n is equal to 3n. We know that 2 minus 3 is going to be. All right. So now do we have the ability, if we said, all right, we just found that definition, let's go ahead and find the 285th term. Could we do that? Just put 285 in place for n. We don't even have to think twice about it. Ben, question?
Last year we used a sub 0 at the first term. Is there a difference between like a sub 1 and a sub 0?
Short answer, no. Again, if you didn't hear what Ben was asking, he said last year at times we used a sub 0 as the first term. Here we're using a sub 1 as the first term. Is there a difference? Again, the short answer is no, there's not a difference as long as we specify which we want to be the first term. In some cases, many cases in fact, it's kind of a personal preference type thing. In my brain, my simple mind, if I'm talking about the third term, I want n to equal 3. If I'm talking, not 2. If I'm talking about the first term, I want n to equal 1. Again, could we write it in a way such that it begins with n equals 0? Absolutely, we could. We just have to document that that's exactly what we're doing. There will be times and places, quite frankly, where it's out of our control, and we have to go about it this way. But yes, absolutely, that is a possibility for sure. Okay. All right. So, quick example here. Actually, it's going to have 4 parts to it. So, as you can see, the sequence, we're told that it's arithmetic, which is very, very helpful. But for the arithmetic sequence, you can see a sub n is equal to 2, 9, 16, 23, 30, ... First thing that they want us to do is find the common difference. So, what are you going to tell me? What's the common difference here? Yeah, I'm adding the same amount to get from one term to the next. So the common difference here is 7. Very good. Next up, we want to write out the explicit definition. So, explicit definition, we just wrote that up on the previous slide. A sub n is equal to d times n plus a1 minus d. So, we know d is 7. That's great. A sub n is equal to 7n plus something minus 7. But what's my first term?